In today's Excel lesson, we're going to set up the explicit finite difference calculations for the free-falling cherry problem that we discussed in class. If you remember, we have a cherry dropping robot that's dropping cherries onto ice cream sundaes as they move past on a conveyor belt. The initial height of the cherry at time t equals 0 is 0.8 meters, and at some time t final, the cherry will land on top of the ice cream sundae, and that position is y equals 0. We want to know how long it will take the cherry to reach the top of the ice cream sundae, and we can, of course, determine this if we know the position y as a function of time. So we want to know y is a function of t, and what we know already are the position y at time t equals 0, that's the 0.8 meters. We know the initial velocity, that's 0 meters per second. Since we're not throwing the cherry, we're simply dropping it. And we also know the acceleration at all times is equal to minus g, a constant, and that's because we're considering a cherry in free fall. Knowing these things, we're going to use the explicit finite difference technique to successively solve for y after one time interval has passed, and then y after two time intervals have passed, and so on, until we reach a value of y that's 0 or very nearly 0. So let's go ahead and set up this problem in Excel. We'll start by looking at the parameters section of our worksheet up here in the top left corner. You'll see that we need to enter values for the mass of the cherry, the gravitational acceleration, the initial height, the initial velocity, and our choice of time step size. You'll see that I've already named these cells, little m for the mass, little g for the gravitational acceleration, h for the initial height, v_0 for the initial velocity, and dt_1 for time step 1. We're actually going to look at two different time steps here and compare our values that we get. So our second time step size, I've named that cell dt_2. Now let's go ahead and put in some values for these various parameters. The mass of a cherry is around 5 grams, so let's convert that to kilograms. So converting 5 grams to kilograms gives us 0.005 kilograms. For gravitational acceleration, little g, let's use a value of 10 meters per second squared just so that our Excel calculations will come out to be like those that we did in class. Of course, it should really be 9.8 meters per second squared. The initial height is 0.8 meters. The initial velocity is 0. And for a time step size, let's choose 0.2 seconds for starters. Okay, let's go ahead and look at the time step 1 section of our worksheet. You'll see that we have columns to enter step number, the time, the acceleration, the velocity, and the position. We'll start by generating step numbers, so we can type in 0 for the first step, 1, 2, and then let's use autofill to extrapolate that series. Now we've got several step numbers to work with. Next, let's enter the initial values of time, acceleration, velocity, and position. So the initial time, of course, is 0. The initial acceleration, and in fact the acceleration at all times, is equal to minus g, so equals minus g, and of course since that's a named cell, we will get a value of minus 10 meters per second squared. The velocity, again, we've got that value in a named cell, so equals v_0, gives us 0 meters per second for the initial velocity, and then finally the position, we'll type equals h to give us our initial height of 0.8 meters. Next, we want to fill in our time column, and since we know that our time step is 0.2 seconds, I could type in 0.2, 0.4, and then extrapolate this series. But since I may want to change the size of my time step, I'm not actually going to do it that way. I will instead enter a formula here that depends on the delta t that I have put into a named cell. So I could either multiply the step number times delta t, or I can add delta t onto the previous time, so I will do the latter. So in this cell I will type equals the previous time plus our delta t, which we name dt underscore 1, and of course I get 0.2 seconds. I can then copy that and populate the rest of the time column. Now you notice that if I go over here and change delta t to 0.1 seconds, all those times do change, and that's exactly what we want to have happen. All right, I'll change that back to 0.2, and we will next fill in the acceleration column. Now this is a particularly easy problem because the acceleration is the same for all values of time, so we can just copy our minus g all the way down for all of the times.